Hello. Uh, so we are live. Let's wait for people to join here. Okay. Hi Subaru. Hi Sak. Am I audible?
Yes.
Yes.
Okay. So let's wait for 3 to 5 minutes to others to join. Then we can start. Okay. So before we join, you do you people want to have a webinar on Keras exercise next week? Hello.
Yeah, would be nice because there was only a few part in the course, and would be nice to know. I don't know if we should know both Pytorch and Keras in a practical way, but it would be nice.
Okay. So
Yeah,
yeah,
and I was
I talked with Isaac on that. So he was also asking about the Keras webinar. So let's see if I thought that the project is on Pytorch, so we will focus more on Pytorch. But seeing that there is enough time for that, we can do a webinar on Keras also. So basically, some model building and stuff. We will do some exercises. Okay. So I don't think anybody else is joining, so we can just start.
if we don't
So
do with Keras, we can also do like TensorFlow or
yeah,
something else.
we can do all these things from TensorFlow, also from PyTorch also. With TensorFlow, what advantage we have is we have control over each and every single node. With
Mm.
Keras, we have like we can it's very simple to implement. We can add layers and networks in a go. And with PyTorch also provides all these functionalities, but it's a whole framework. We can do much more things here. Also, we can run codes on GPU using the two device command in that is there in PyTorch, and mostly people nowadays use PyTorch. So that's basically the reason that it's covered in this nano degree. Okay, so yeah, let's start for today. So today is our sixth webinar. We will be doing some PyTorch exercises, and my major aim is to do the transfer learning exercises. Exercise that is the sixth exercise. Eighth exercise. So let's talk something about transfer learning. So it's a machine learning technique where a model is trained on one task and is retrained or repurposed for a second related task. It has many applications, like for in my line of work, I use transfer learning when I am training my robot. First I train my robot on a simulator called Gazebo, and then whatever model I get from training, then I run it on the real robot, and then I tune the model further so that it adapts itself to real life environment. So that's how it works. Also, in if we talk about images, then there are multiple networks that have set the standards for this image features processing, like ResNet and VGG16. They are quite good models, and they are trained on ImageNet data. So ImageNet is a huge data set, thousands. So there are multiple classes and many images. So we can use those models, and then we can tune them further for our cause or our work. Let's suppose you are doing something like, if I have to talk about something from the perspective of a robot. If a robot is seeing things, it has to identify things. If I have a pre-trained network called ResNet, which is trained on multiple different images, which my robot then can use to understand and extract the important feature out of images, and then it can tune the model accordingly to its need. That's how we use transfer learning. So basically the the fundamentals of transfer learning is that we first train a base network on a base data set, and the task also, the base task, and then we repurpose the learned features or transfer them to a second target network to be trained on a target data set and target task. So this process will tend to work if features are general, meaning suitable for both base and target task. So there should be a relation between them. Otherwise, the pre-training won't work. So there are three steps. First, we select a source model, then we reuse the model for new task, and then we tune the model. Right. Okay. So let me now share my screen. Then we'll just jump on to some exercise. So yeah, I guess my screen is visible to everyone. So this particular exercise is your transfer learning exercise in deep learning with Pytorch, right? So I have completed that exercise, and we will gonna discuss that we are gonna discuss. So um, in your exercise, in your module, when you see that there will be many these things will be blank and you have to fill them yourself. So I have completed this one and some exercises from the previous also, previous sections, and then this will give you some idea on how to proceed with some such exercises, right? So before that, okay, so transfer learning, they say that ImageNet is a massive data set with 1 million images and 1,000 categories. Okay. Here we are gonna use a network trained on ImageNet dataset, and then we are gonna use it for binary classification for our cat and dog model, the cat and dog dataset. So we have a data where we have images of cats and images of dogs. We have to train a model that can differentiate between cats and dogs, right? Okay. Um, so this is good, and then we import it. Okay, and so here it is saying that these are the means and these are the standard deviation value that you need to do transformation. So basically the formula is any data set, any data point x minus mu is these points. So this is one for each channel r, g, and b, and then there are standard deviation for each channel also. So the formula is x minus mu r upon sigma r, that is red channel, x minus mu b upon sigma b for blue channel, and x minus mu g upon sigma g for green channel. Right. Okay. So this is the transformation that we define. You must have seen in the lessons itself that before doing any before passing the network to the before passing the data to the network to do the feed forward, before we can apply many pre-processing methods on the data set. Earlier before the deep learning part, we used to do it on the pandas, and we used to do things like that. All those operations can be done using this transform function. So here I list out the functions that I need to run sequentially one by one on the data set. So whenever I load my data set with these transforms, it will apply these operations. So here random rotation of 30. So basically this is my training data, so I want it to be as random as possible. So I'm applying random rotations. I do random resize of cropping. So I apply the crop. I have cropped the 224 out of the image, and horizontal flip. Then I convert it to tensor. So all the operations will be done on my tensor, as you know, in Pytorch. And then I have given these, I have been given these values that I apply. I do not need to do random on these things because this is my test transform, right? So in test transform, we already we do not need as this random thing, because for training we want our model to be as general as possible, but for testing it's not required. We can do these operations here also, but it is not required, right? Okay, so this is the part where we load the image, load the data set of images. Here I guess we have a whole exercise on that. So yeah, so let's go through this exercise first. Okay, so here we will learn how to load the image data sets. So we have data set with dog images and cat images. So let's run them one by one, right? So import all these library. We are importing matplotlib because we are gonna see the pictures that we have imported from the data set. Okay. Okay, so these are the instructions that are there for this particular thing. Before doing this exercise, you will be reading this part. So we have done this much and this much. For data loader, you can understand itself. It as a iterator. For example, in data structure also, when you have maps or something, you can create an iterator to run on that specific data type. So similarly, we have data loaders. So we pass the data set to it, and batch size and shuffling. This we may pass or not pass. So but when we pass through, then the data set is shuffled randomly. So basically I have a set of 32 data entries from my data set in each iteration, and then I can pass through it, right? So here you can see what I do. So I resize the data, I resize the data image, and I crop it, and I to apply to tensor. These are all I followed it from these instructions. And then I load my data from data directory. Data directory is my cat dog data, and in that there is train. You have this on your workspace, you can run this site simultaneously. Okay, and one more thing, maybe I am running on GPU right now. Okay, so it's okay. I have so in your GPU version, you must have 60 hours. So you have to use them very efficiently to complete all this project and exercise, right? Okay, so here I am creating the data loader object for it. I am passing the train data, I'm passing the batch size, and the shuffling parameter. Now when I have that, I iterate through the data loader data set, and I get the image, I get the label, and then using the IM show part, I show the image, right? This time it is different. So when I run it again, it will be different because it is iterating to the next part of the data loader every time I run it, right? So there are 32 images for each iteration, and I am printing the zeroth image. I can apply this also, right? So image zeros are giving me dogs, image one is giving me cats, right? Okay. Now now that we have done it, we will go through that. Okay, so you will see that this is the formula that we apply to normalize the data set. We also did some normalization before deep learning also. There was min max scaling, and there was this normalization. Similarly, the concept is the same, right? Okay, so here I define my transforms. I give the values 0.5. So these are some random values. I now again load my data and create two objects: train loader for my training data set and test loader for my data set. Shuffle I have not done here, but I could do. So by default it is false. Okay. So I run it now. From here you can see that the directory here was cat dog train. So I just passed the directory directly. But here my directory was defined as cat dog data. So I had to add this block here, that I need to go to the train part of this to make the train data set. And then I create the train loader object of this train data set, right? And now we just iterate through the test loader. You can do the train loader here also, right? Okay, see whether it works, and then you can just run. Okay, so I am showing four images here. So four images of this data set, right? If I Right. Okay. So I just to see that whether my data loader iterator works or not, I create the train data loader object, and then I iterate through it, and then I show the images. Right. So this is the exercise you will be doing. So there are total 8 exercises. Validation is the eighth part. Say, okay. So I had this somewhere. Yeah. Yeah. Learning with Pytorch. Workspaces. Let me see. So as far as I remember, this was the last exercise. Okay. Yeah. So there are so transfer learning is the last exercise here. These are some basic exercise 1 to 4 and fifth also, and sixth, seventh, eighth I am covering in this webinar only. So you will find these one quite easy as compared to this one. Right. Okay. So here they are saying that your transform images would look like this, and they are okay. So here I have created my own network. So this is optional to do. You can do it or not. I would ask you to do it if you want. Right. So I create a network. I pass the images which are 224 cross 224 for 3 channels, and then in the second layer I created 784. I could pass any number here. I could pass 256 also. The training, the size of number of nodes in a particular layer do matter in the accuracy, but we do not have a fixed rule for that. Uh, but there is a balance between them. If this number is quite low as compared to this one, there can be a tremendous amount of loss of data. But if this number is is equivalent to this number, like this is 100 and this is 90, then there is not much of feature extraction. So there should be a balance between those two, right? So here I have done 784. I could do 256, but it would have resulted in a big amount of loss of data, right? I have completed this training. I can run this again, but it will take quite a lot amount of time. Then I applied relative ReLU, we say that. So ReLU is basically if a function is the formula is it if it is negative, then it becomes 0. So max of 0 comma the value. If it is negative, it becomes 0. Otherwise the value is x. So max of 0 comma x. So if it is more than 0, it remains as such, and if it is negative, it becomes 0. So what's the point advantage of ReLU is it does not suffer with the problem of the vanishing gradient that happens in the sigmoid. So there, when doing the deep learning derivations, you must have seen that they were deriving the back propagation formula, and then they talked something about the vanishing gradient part. So actually the sigmoid function in each iteration reduces around to 1/4 of its part, because the maximum value that a derivative of sigmoid can get is 1/4. After a few iterations it becomes the gradient becomes zero, and zero or negligibly small, and the derivations do not keep on changing, gradients do not keep on changing. So we do not suffer this problem here in ReLU. ReLU has different sort of problems. It has okay, so this is something that you can check out. uh, what was it? I guess it was disappearing. ReLU. So here what happens is, I do not remember the name. So this was something like that only. It was vanishing ReLU or something. I'll have to check. Okay, so it was dying ReLU. The concept is that in the dying ReLU, what happens is many nodes become dormant. They do not update with the propagation, and that's so this is similar to dropout also. But in dropout we ourselves give us a fraction of the nodes we do not want to run further. In ReLU, after a few iterations, it happens is after many iterations it happens is that few nodes become dormant, and that's called the problem of dying ReLU. It's not as dangerous as vanishing gradient problem. So most of the networks today use ReLU, right? Okay, so I then apply this 784 to 128, basically the linear reshaping of the data, uh, or there are perceptrons to it, and then apply ReLU, and then this, and then a ReLU, and then this linear, and then softmax. And so after that, I run it for 5 epochs. I run through the train loader iterator. I see the images. I do the zero grade part. So zero grade is something when you do not want so for each epoch we want it to start from the beginning. So we do not want it to be changed every time. So that's how it works. So we can also check it here. Optimizer dot zero grade. So a standard definition of it. Okay. Okay, yeah. So gradient is accumulated every time the variable is propagated, and so for each epoch we try make it such that so the gradient is not accumulated by this command, grade dot zero zero grade, right? For each epoch, for so this is for each data this is happening. So gradient is not being accumulated, and then we forward the images, and we um, compute the loss, then we apply back propagation. So you see back propagation is quite easy here in Torch. You just need to do loss dot backward, and then do optimization. Here I'm using stochastic gradient descent. People you may use Adam also. And then I add the losses for each time, and then I divide it with the length of my train loader, right? So you can see that after a few epochs, here 5 epochs, my data loss is quite less, right? Yeah, so that's it. So this is the optional part of this exercise. You may do or not do. So this is something that I did to show you that how can we create our own network and train it. So this is not very hard with Pytorch. In last webinar also we did something like that. So then we can go to, okay, then we can go back here. Here we apply the transformation and stuff, right? So this is I have completed this exercise here. So my training has already been run. We can run it again. Okay, so this, yeah, we can run it again, but it will take quite lot amount of time. One of the students also asked me that it is taking too much of time. But yeah, it happens here because the images, the data is huge, and the network itself is quite lengthy. So let's see. Okay, right. So here we are running the dense net data set. This is not showing properly the dense net. We can see basically we would like to see the dense net architecture. Okay. Yeah, so this is quite dense really. Okay, so here they have the in each dense block they have a small neural network for itself, and they are adding them and stacking these neural networks called dense blocks, and this makes the whole neural network called densenet. This is also trained on ImageNet dataset. So if I have to see the accuracy comparison, dense networks on ImageNet, then we can see, yeah, ResNet, LXNet, VGGNet, these all have this comparison we can see here. You can see that they are also using ReLU because of the vanishing gradient problem. This is VGG16. This is something that I have also used personally in my project. And this there is Google Net, there is Residual Net. There are lots of them. So you see, there is top one accuracy, the highest accuracy that a network can get, LXNet, VGG. So VGG is getting the highest top one accuracy. Top five is the top fifth best. So bestly predicted elements or data elements, and then VGG was leading in this one also. Okay, ResNet 50 is better than VGG here and also here, right? So ResNet 50 is performing much better, and then VGG is performing second. But there you can see the number of parameters: 61 millions parameters, 138 millions, 7 millions. So for that, Inception is quite good because it is taking less parameters, right? Okay, this part we have done. Saving and loading also we have done. Right. So let's see the architecture first. Yeah, if you run it, you will see that in DenseNet, first they are doing this convolution, the ReLU, the pooling, and then start the dense blocks that we saw here. This first dense block here. So this dense block has normalization part, ReLU part, convolution. So you can see that it's a whole neural network on itself. So DenseNet is basically the stacking of different neural networks. As you saw in the ensembling techniques, in ensembling techniques, we take the collective of different classifiers, and then we using those the aggregate of those we try to improve the accuracy. Similarly, then there is dense layer 2. You see that the batch norm size and the convolution layer size is different in both of these, right? But final output is same. Okay, so here this is different, this is different. So they have six dense layers. So how many did we see here? We saw here only three. So there must be someone with six layer. Yeah. So this has five. Okay, so they are showing them uh, this way, right? These are dense layers in between these images, right? Dense layer 1, this is the image block. You see this is 224 cross 3, and after that it becomes cross 64 because we apply convolution on it. So we will also discuss about convolution neural networks later in webinars. So I guess this is not needed right now. And finally they apply this to find the softmax probabilities. Okay, so here we have this network, dense layer, dense layer, dense layer. So this is quite heavy. Dense net 121 it is set. Okay, okay, right. So this is done. So basically we imported the models from Torch Vision. It has um, different such networks, testnet, VGG, and this dense. Okay, yeah, here comes the part. What right now we are doing is now we have a trained network that will extract out the features of the images. Now using those features we want to build a classifier which will classify our images according to our own data set, right? So first of all we need to set the parameters that requires gradient equal to false. So what this means is that we are not going to change the parameters of this dense net. Okay, so this is already trained. We only want to change the parameters according for the classifier that we are building. So we stack our dense net with our classifier and then predict, right? So here this is my layer name fc1 relu fc2, and this is what this is doing. So it is giving me features in the form of 1024 cross 1. Yeah, that we saw it, 1024 cross 1. So the input should be 1024, and then the second it gives the output 500, then 500 to 2. So we have two probabilities, right? For either cat or dog, we take the maximum of them to understand which one is which, right? So you can try to tweak this by applying different number of nodes here. So basic idea that that I have used here is so 1000 to 500. So I have halved the number of nodes here, right? Okay, so this exercise is also there. So this is basically for comparing the difference time difference while running the training on CPU device and the CUDA or GPU device. So we have this command called model dot to, right? For what we do is we define a device and then we pass it to model 2. So if it is CUDA, then it passes with GPU. If it is not, then it runs with CPU, right? So we have only two options. We run for both of them. Let's run it, then we will see the time difference between these two. It is said that GPU makes it approx 100 times faster for ImageNet datasets. ImageNet is huge dataset. It cannot be run on CPU. But here we have the cat and dog dataset that we have imported here, right? Okay, so we are using that from train loader to passing the we are passing it to model that we have defined here. So a model already have, we have added the densenet as our model and then added classifier to it. So we are running those images on this model, and then we are trying to see the time difference between those two. For this is for single epoch, right? Once for CPU and then for CUDA. So let it run for a while. It will give us some values. Okay, so I have my GPU enabled. It will. Okay, so CPU time is 5.5 seconds, and you can see the GPU time is 0.01 seconds. So that is approximately 500 times, right? And now this is training part. So this is I'm not gonna run because it will take a lot of amount of time. So this is what you will be also doing. You are this is a to-do task for you using a pre-trained model. So I can go through the steps for these for you. Yeah, so here I define the criteria for calculating loss. So this is something that we can Google, then understand what it is, right? NLL and triple L loss function. Okay. Usually we do not. I particularly did not ever dig into this NLL loss data set because I know cross entropy. We all know MSE. We all know L1 loss, L2 loss, cosine similarity. So there should be a. Yeah, just okay. So this is my NNL log, or this is my cross entropy. This is my cross entropy. This criteria combines with and log softmax and the NNL loss. So basically this part, right? Okay, so this is my function for this NNL loss thing. Okay, so this we could change our loss criteria accordingly. We can do MSE or this. I have so this is quite useful for such image type of data. Okay, so here you see what I have done is, so torch.device is CUDA. If CUDA is available, so I have done it as enabled. I am running it on GPU mode, so it is available. So it will be CUDA. Otherwise, it will be CPU, right? And optimizer I have used here Atom, not stochastic gradient descent. Atom works better. And then I pass it to, then I pass my whole model to the CUDA, right? And so for I in range epochs, I put running loss equal to 0, and then for my training data, I pass my inputs and my labels. I have to manually pass them to my CUDA device. It's not natural for it to run with GPU unless you pass the inputs and labels to GPU also. You cannot. You will face an error when you pass the model to the GPU and not the inputs to the GPU. Then this is the comment that I have put. So this is why we are doing it, because we do not want the parameters gradients to be accumulated. Then we forward our input to the model. We compute outputs. We compute loss. We apply back propagation. We then apply optimization, and then we add the loss that we are getting, and then we print it, right? So this is the, when I run it, you can run it, but I have also already run it. So this is my data, this is my epochs. So this should not be 100 here. So 100 is basically after every 100 step I'm printing it, but here when I'm doing loss I have to do it for the whole epoch. So the train data, this is something wrong here, but it's okay. Yeah, this is and then testing. Okay, so now before testing, okay, so Isaac has left, I guess. Okay, so Subaru is only there, right? So before testing we need to also save the model, right? So there is whole exercise for saving the models. Let's go through this one also, and then we can do go to the testing part. Okay, okay. Yeah, first part is importing. Then same as earlier, here we are importing the fashion MNIST data. We are creating the iterators for training and testing, right? uh, then we see the image. So you can see that this is a dress kind of thing. So this is the sparse data set for fashion images, and then we train the network. So we already have this FC model from Torch. FC model, what can it do? It can create a network itself. So like you have Keras, similarly you have FC model. You can see that you are passing the number of layers, number of nodes for each layer in the FC model, and you are passing the criteria. You are passing the optimizer, and then you run it. Okay, so the first epoch, the training loss is this and this.
Vilena?
Yeah,
Can I ask,
Swarup.
can I ask one question?
Yeah,
So
sure.
when you train or like a picture or like I mean MNIST data, like the numbers, you flatten data, right? Structure.
Yes.
In this process, you ignore the color.
Okay, so MNIST data is not color data. It has only this grayscale images.
So that's why you just take
Yeah.
2 dimension.
Yeah. Okay, so this is the training is running fine. Okay, then the main purpose is the saving model. So after we are done with the training, we need to save our model. So there are few things that we need to save: the parameters, the state of the network, and the checkpoint, right? So the state where till where the network was saved, trained. So our model is this one, and their model of the dictionary is basically the state of the model in this part. So you see these are the features of the network, and when I print it, this will be printed like that. Okay, so here this part is already, I should stop it run. Okay, so let it run then. Okay, now it has run. So this is my, these my networks are also stored in my when I save the model, and now I can save it using the extension Pth. We can also save it using extension T7, and there are several kinds of extension of the model that we have. uh, so there is also MBL, PKL, and those sort of extensions. HT5 is also there. So now I am loading my saved model itself. So now I can run the testing on it, right? Okay, so now here this part is where we have to see that the way we have saved the model and the input that we are passing after loading it should be consistent. So I am also saving with my model the input size, the output size, the hidden layer sizes, right? And I call it as my checkpoint. And when I run it, I then load my checkpoint. Here now I am loading my model and running my image. I'm not here running it. I'm just loading here, right? With the checkpoints. So checkpoints contain the sizes of different nodes that I need. So that may help me when I am passing the new data set. Okay. Right now. Okay. So now after doing the training, we can say go to saving. So what I do is I save my model using this. I give the number of epochs that I need to run. I give the parameters that it needs to access and the optimizer parameters, and then I save it as my train model.pth. And whenever I need to load it, I load it with this way. So now, and when I have my train data, how do I run testing? So I define the criterion as same as above. So these are the standard step. With practice, you will be quite familiar with it. You will be applying it everywhere. So you define the criteria, you define the device, you define the optimizer. These are the three steps that always come together. Then you pass the model to the device. Then I run with no grad value. I run with on test data. I pass the images to device and labels to device. Then I compute the output, and that torch.max. What torch.max does is, so if I have two probabilities, is it will tell me which probability is it. So this one tells me the row size. It tells me that I have to find the maximum value for each row. If it has been 0 here, it will find the maximum from each column. So my data entry comes as a row. So it will find me the maximum probability. So I have two probability A and B. If my probability for class 1 is greater, it will be predicted as class 1. If my probability of class 2 is greater, it will be predicted as class 2. I found the total here, and then I uh, compute the accuracy. So this one here has less accuracy here. uh, but yeah, was a simple network that I built. You can also optimize it. Okay. So apart from, so we have done the transform learning here. You see that we covered the loading images part. We created our own network. We imported the densenet data set, densenet network, which is trained on ImageNet, and then we uh, stacked it with our classifier that we made, and then trained on the data set, then saved the model, and then we can run a testing on it. So I already have run it. I won't run it again because it will take too much time here. Right. So now we can go to the project then. Yes. So this, where is the project? Let's see different sections of the project that you need to complete. Image classifier. So I'll run it on GPU. It is taking some time to load. This is same for everyone, I guess. This is since mm, this is the server that Audacity server that I am trying to access. It takes some time to download and starting the project in GPU mode. I have done it. So I've already spent my 3 hours of the GPU time. Okay, so now in this project we have the first part of project is that we have the flowers images. We need to process it, train the image classifier on dataset, and use to predict our image content. Right. So this part is easy. This is just importing. Loading part is also easy. We just now we did all the loading stuff. So this will also be fine. And then we just map this you need to run as it is. There is nothing you need to do here. Here you need to build your own network, right? So how do you build it? We already see how in the cat part we built our own network using this thing. You can do the same. You can or you can you if you want to put a name on your each layer, you can do this order dictionary, right? uh, do this thing. Okay. So here you will be building your network the same way we did there, and after that you will be testing it. You will be saving the checkpoint just like we did here. This way you will be saving the checkpoint for the data set. So I guess all the parts of your project are covered in this in today's webinar, right? We did all loading the data, we did training and testing, we have done the checkpoint, and then there is pre-processing that is done by the transformation function. So there is not much to do, right? So you can see here I did not go through this, but yeah, this part is seems just like that, the transformation function part. Then you do the prediction as we did earlier, and yeah, then you just do the IM show of the top 5 classes. So as we saw, the top 5 accuracy is the top 5 classes that are getting the maximum number of labels correct. Yeah, so this is pretty much the part one of your project. That's not very hard, and I think we completed all the sections of it. Then we can go to the second part then. Okay, so second part is to make this model into a command line interface so that others can also use it. So like you have this Python model that you have created using your data set and in part one, but you want people to import it just like we import the libraries. You want people to run it on their data sets also. So this is what the part is about, in the command line part. So the workspace is also different here. See, this part we can discuss maybe in the next webinar, but I don't think that would be much difficult. So once you are done with your image classifier part one part, you try to see whether you are achieving the same level of accuracy that they are having in their examples. If you are, then it's good, and if you are not, then try to tweak the number of layers in each node. Try to check it with different loss criteria and different optimizing parameters, right? Okay, so this will take some time to load. So if I have to see, okay, so Subaru, you are on lesson 4 of this part 3, right? You are done with Keras and you are doing going with Pytorch. So
Yes.
I guess after this webinar, you pretty much have the idea that there are that's Pytorch is also not very difficult. We have everything in the libraries. We just need to call it. The only thing that we do is pass these parameters, the number of nodes here. Rest
But
everything is taken care of, right?
I guess so. And the question, can I have like a really basic question? How does it
Yeah,
work?
yeah, yeah.
I mean, so you will
How does
divide.
which work?
How does the image classification works? So you separate each pixel, and what kind of information is
Okay.
it's
No,
like
no, no, no.
color
We do
or
not. We do not separate. We do not separate each pixels. We try to find the features in the image. So this ResNet or DenseNet that we are importing, it finds out the features from the image. So it is
what
not
about what kind of
what
feature?
kind of features. So let me tell you. So let's say if you have an image of dog, right? So it will try to see that the dog image has the curvatures around its ears or nose, right? The contrast between the surrounding pixels, and the shapes and sizes of eyes and noses. So these are different things that we humans can understand in an image, right? We can see where the curvature or where their curves are there in the image. um, so for example, okay, let me show you my example. So if I have MNIST data set, so when you pass this data set, so this will give me the feature that image has this part in it, and this part in it, and this part in it, and this part in it. So this zigzag part here, and this rounded shapes here. So basically it divides the whole image into few structures, that it has some curves, it has some linearity, is it has some difference between its surrounding pixels. These are the features that a image can have, that are extracted from the network that we are using, the DenseNet or VGG16 or something, right?
So
Then now that we have those features, we can see the features of cat image and dog image will be different from each other. And which so let's say I have a matrix of features, right? So whenever I pass a new image, I will get a whole different matrix of features. I then compare this metric with my trained matrices of cat and dog. and whichever it is close to, I will assign it to that class only.
That means the input data should have the same format, right? So maybe 28 by
Yeah, yeah, yeah,
28 pixels.
yeah, yeah, yeah. So it has the same format. After training, it understands that this is the majority features that for this class image will be having, and this is the majority features that this class image will be having. And whenever my new image comes, it compares them with both the features, and whichever it is close to, it assigns the new entry to that class. Okay, so part two is not working. So part two is quite straightforward. You will be finding it quite easy now after this when you do it, right? So this is connection failed. I don't know why. So yeah, that's all for today. Next time you want to discuss Keras, right? So we will be discussing Keras. Um, Maybe we'll keep the half part of the webinar for Keras and half part for the project something. Yeah, we'll. I think I'll see that. What are the different contents that we need to discuss? Maybe we can try some stacked autoencoder things. Autoencoders are not discussed in this nano degree, I guess, and those are pretty important for image compression techniques. So, for example, when you have an image and you send it to me through the WhatsApp, it is compressed. So basically, all the essential features of the image are extracted out, and all the rest of the entries are removed. Then that features that WhatsApp has extracted it from the client side, it expands it to the image of the original size. So you see that there is a loss of data, but the there is a effort to keep out only the non-important data from the image. This way we are able to reduce the size of image without losing out the most important features of it. So maybe this is something that we also can discuss, maybe in webinars also. So yeah, that's all for today. Best of luck for your project.
Thank you.
Okay, thank you. Bye.
Thank you. Bye.